Alright, well, today we're going to talk about momentum, which is going to be foundational for the next two programming labs, the Pong game and the Planetoids with Momentum. Before getting into all the jargon and the math and all that stuff, I'd just like to show this video, which is from an experiment where these two carts come in. Hopefully you can see that they're coming in at basically the same speed, but in opposite directions. And then they collide with each other, and one of them is heavier than the other. In other words, more massive. And I think it's not too hard to see which one is the one that's more massive, right? So it seems pretty clear that this would be the one that is more massive, especially because this other cart goes zipping off to the right at high speeds. And actually, if you look closely enough, you can see there's some extra masses on top of this one holding it down that are not on this other cart here. So it's not too surprising that the cart on the right goes zipping away. What's more interesting, I think, is the fact that in this experiment there is a little force probe on this thing. So the more that this is compressed, the more force that it registers, and you can see that force on the screen here. And I don't remember which one is which, whether this one is that one and this one is the one on the right, or whether it's vice versa. But the other remarkable thing from all this is that in spite of the fact that one cart is much heavier than the other cart, the force that both of these force sensors read has the same maximum, and actually even the same shape. And so the force as a function of time is actually the same, at least in terms of the magnitude. I mean, the forces are on opposite directions, but again, the magnitude is the same, which is kind of remarkable. So we're going to use that in just a minute. So what's remarkable about this is that so far in the course we've only been doing situations where the force is constant. So weight is constant. So my weight is pulling me towards the ground, but that weight isn't really changing with time. Even if I jump up and down, it doesn't really change. We've talked about friction, so kinetic friction, for example, that's a constant force opposite to the direction of motion that's there until you slow to a stop. So that's a constant force. Another example that we did was the fire extinguisher cart. And so the fire extinguisher would accelerate off to the right with a constant force. So that's what we've been doing so far. We've never actually done a force that changes with time like this, and is not just going up to a constant that has some shape to it. But the nice thing is that in these situations we know that the two objects, the two carts interacting with each other, those forces are the same with time, and this is actually a manifestation of Newton's third law. So we talked about Newton's third law a while ago, that if I push on something, if I push on this wall, the wall pushes back at me with the same force. So this is another example of that we can use. So again, the forces are the same as a function of time, at least in magnitude. So this is kind of ignoring the direction, but so the forces are the same. We know that F equals ma. So this is the mass of cart 1 and the acceleration of cart 1. So we can solve for the acceleration of cart 2, and that involves a ratio of the two carts. Remember, cart 1 is more massive than cart 2. And so m1 over m2 is going to be a positive number much greater than 1, probably. Which means that whatever acceleration that cart 1 has, again, this is all just magnitudes here, whatever acceleration that cart 1 has, cart number 2 is going to have much more acceleration than that. So that's what we know so far. What we would like to know is we would like to know what the final speeds of the two objects are, v1f and v2f. Right now, all we have is a1 is a function of time, a2 is a function of time. Maybe we also know what the initial velocities of the two carts are. And so if we have that, we can actually use that to figure out what the final speeds are, like this. So we have some initial speed, and this is all sort of in the x direction. We have some initial speed, and then there's some acceleration as a function of time. But if we can figure out the average acceleration here, then multiply that by the number of seconds that the two things are in contact with each other, that will tell us what the final speed of object 1 is. And likewise with object 2, because we know what the acceleration of object 2 is as a function of time. We can figure out what the average is, multiplied by how many seconds that the two are in contact. That will tell us what the final speed is, heading the opposite way. So there we go. So we haven't been able to deal with forces that change with time, but if we can just figure out what the accelerations are with time, figure out the average multiplied by how many seconds they're touching, that will give us the final speeds of object 1 and object 2. So the only reason we were able to navigate that last case with the two carts bouncing off of each other is because we knew what the acceleration was as a function of time, and we knew what it was because we had a measurement of the force as a function of time. But in general, we don't always know those things. So for example, when you're shooting a gun, like that, we don't always know what the force of the gun on the bullet is as a function of time. And unless the bullet has an accelerometer on it, we don't know what the acceleration is as a function of time. So your phones have accelerometers on them, which is how they can figure out what direction they're sort of oriented. And you can actually get that information if you download the right app. But in general, not everything has that accelerometer on it, and we're often thinking about charged particles that are deflecting off of each other. I mean, clearly you're not going to put an accelerometer on the charged particle. That doesn't make any sense. But we need some way of navigating these situations, even without this information. There's other situations in which there's energy as a function of time, power as a function of time. There's other situations in which we don't know that either, and we just need to be able to have a way to use the information that we do have. So in this next example, we're going to do that, and I'm not going to go at it from the angle of, all right, here's the momentum, and I'm going to apply it for you. Just to give you an example, what I want to do is I want to explain how do you use the information that you have as best as you can, and then go back and say, all right, this is how momentum works. So I want to explain momentum without saying the word momentum, so hold on tight. And what we want to do is that we want to be able to ultimately predict what the kickback speed of this gun is based on the bullet gets fired. So here's the bullet. There we go. Barely missed. All right, so the gun slides backwards, right? The ultimate purpose of doing all this is trying to figure out at what speed this gun slides backwards. And the only information that we really have is the speed of the bullet that exits the barrel. And so we have to think about this. We have to break it down. Okay, so here again is the bullet. There we go. Dodge it. All right, there we go. So we don't know what the force as a function of time on the bullet is, but it has to be something, right? So it might look like this. So if we did know the force as a function of time on the bullet, we could figure out the acceleration by dividing by the mass, right? So the acceleration is the force divided by the mass, and so I'm sort of drawing the acceleration more exaggerated here because the mass is very small. The mass of the bullet is very small. So all right, that's fine. So that's the acceleration as a function of time. How do we figure out what the velocity is as a function of time? Well, you could do that by calculating the area under this curve. So imagine that we're putting these little rectangles here, and we're going to add up all the areas of these things, which is the height of the rectangle times a little delta t, the time interval over which each one is there. Mathematically, doing that sum, adding that up, looks a lot like this. And so where this is the height of the rectangle and this delta t is the width of the rectangle. So that's the only so that's how you sum that up to get the final speed. This is the speed of the bullet, by the way. And so the speed of the bullet is going to look like this, right? So if you add this up initially, it starts at 0, right? Because you haven't summed anything up yet, and you sum up more and more and more and more and more. The velocity gets faster and faster and faster. And so what this means is that if we have the final velocity of the bullet, if we can measure the final velocity of the bullet, we don't really know what the acceleration is as a function of time, but we do know sort of like what the area under this curve is. We do know something about the acceleration. We're not totally ignorant to what the acceleration is. We just don't know exactly what it's doing as a function of time. So what we're going to do is we're going to use this information as best we can to figure out sort of what the kickback speed of the gun would be. So hopefully you can see from this video that the gun is sort of, pushing back on the hand. So, and this guy's hand is sort of absorbing that kickback. If it wasn't for holding it, then the gun would slide backwards and things like that. So usually in this video, I ask students if they think I've ever shot a gun. In fact, I have, and I was genuinely surprised at how much it pushes back at you. So if you've ever shot a gun, you know that very intimately. Anyway, so we're trying to figure out how quickly that gun, what that velocity that the gun starts moving back at, that velocity that your hand has to absorb. And so we don't know much about this situation, but we do know that Newton's third law applies, which is that the force of the gun on the bullet is the same as the force of the bullet on the gun. Again, in magnitudes here, not necessarily directions. We know that the force equals the mass times acceleration. That's Newton's second law. So we can solve for the acceleration of the gun, and we know that the mass of the bullet is much less than the mass of the gun, so this has to be a factor that's much less than 1. It's a small number, and this is the acceleration of the bullet. Now, again, if we had an accelerometer, we might know this information, but we don't. We only know what the speed of the bullet coming out of the barrel is. And so what we can do is we can kind of do this mathematical trick, and we can sort of sum up. We know that this is true, that if you sum up the acceleration with time of this thing, you get the velocity of the bullet, and this is a measured quantity. We also know in principle, if you sum up the acceleration of the gun with time as it's being shot, that would give you the final velocity of the gun. And this is really what we're trying to figure out. So what's interesting is that if you sub this into here, like this has to be true, the sum of the acceleration with time times the time interval gives you the final velocity of the gun. So if you sub this into here, you end up with this, right? So that the masses are just constants you can take out of it. And so you get this sum of the bullet versus time. Well, that looks familiar. This sum is just that, right? So that's just the speed of the bullet. Okay? And so if you put it all together, you end up with something like this. And so all you need to know is the final speed of the bullet, the mass of the bullet, the mass of the gun. That should tell you what sort of the kickback speed of the gun is going to be. So there you go, we did it. Now, in a minute I'll talk about how this makes sense in terms of momentum conservation, but hopefully you're impressed that I didn't actually use the word momentum conservation to do this. It's just sort of, this is what you get. The point I'm trying to emphasize at this stage is that when you start with something that's fairly complicated and you end up with something very simple, that often means that there's some sort of conservation law or special law going on. So we haven't talked a ton about conservation laws, but the simplest one is just mass conservation. So if you put 10 kilograms of something into something else, then the weight of this something else should go up by 10 kilograms. So that's mass conservation. So that's fine. We've talked about energy conservation. There's, even when there's friction, the total energy is conserved, and so that's fine. So energy is conserved. We came up with this formula. We started from some fairly complicated things and ended up with something fairly simple. It turns out that the thing that is conserved here is the momentum. So what I want to do is I want to derive this more properly, and I want to make sure that we use the vectors now. So this is actually from Downton Abbey, which the first season is pretty good. The rest is a little bit annoying. But anyway, so we're going to do this properly, like a proper dinner table type thing. All right. So we know the acceleration is related to the velocity, right? So the mass times the acceleration is the derivative of the velocity. So mass times acceleration is dv dt. And then we also know Newton's third law, which instead of just setting these two things equal to each other and just saying, okay, that's the magnitude, now it's actually include the fact that, when I push on this wall and I'm pushing this way, the wall pushes back at me the opposite way. So there has to be a minus sign there. So that's fine. And so if we sub in what we know about we sub this into here, we'll get something. We'll get something like this at the end of the day. So you notice on this previous slide, I pointed out to you that the mass can be out front because the mass is a constant. It can also go inside. So that means that when we do this and turn it into this, and substitute in that dmv dt thing, that ultimately works out to mean this. Now, in calculus, whenever something inside of this thing, whenever the derivative of something is equal to 0, what does that mean about this thing? Don't say 0. It might be 0. What it means about this thing is it's a constant, right? Because the derivative of any constant is 0. And so just from Newton's third law, just from this thing, you end up finding that, this vector quantity plus this vector quantity adds up to a constant. We are going to call this constant the momentum, in particular the total momentum, and mv1 and mv1 and m2v2, these are the momenta of object 1 and object 2, and so p1 and p2 there. And it's a vector quantity, so energy is not a vector quantity, but momentum is, because it has to be moving in a particular direction. Momentum is essentially because the velocity is a vector quantity. But again, we're going to call this the total momentum. Okay? Now what's interesting about this is that it means that the force is the mass times the derivative of the velocity with time, or dmv over dt. Well, that means that the force is the derivative of the momentum with time. And that's interesting. And that gives you there's actually some interesting things that you can learn from just this relationship itself. So let me give you, before I sort of jump to how you can use this to do some interesting stuff, let me point out to you that earlier we were doing something like this where, remember there's two carts that were bouncing off of each other. There was some initial velocity, there's some average velocity, there's some time in which they're in contact that gives you the final velocity. So we derived that essentially from the fact that the acceleration is dv dt. So in other words, the acceleration is dv dt. That means the average acceleration over some time interval gives you the change in velocity. So we can do a similar thing here, and we can say that, well, the final momenta is equal to the average force times the time over which the things are in contact with each other, or over the time at which this force is being exerted, you could say. Again, this comes from the force as a function of time is dp dt, and this came from, this is dp dt, and this came from dv dt. So anyway, same sort of a deal. Now, in the language of this course, in the vocabulary of physics, this term is called the impulse. Okay? Obviously, this is the initial momentum, that's the final momentum. This is the impulse. The impulse is essentially the change in momentum over some time scale. And it's an interesting thing because, so the change in momentum is the same thing as the impulse. And it's an interesting thing because what it means is that the change in momentum can be the same, but if the force is over a much longer time scale, then that force can be, the average force can be much lower. So a classic example of this is throwing an egg into a sheet. And so they're going to throw eggs into sheets as hard as they possibly can. So this guy is really giving it everything he's got. And you'd think that the eggs would break, right? But it doesn't. And the reason that it doesn't is because the time over which the egg is being slowed down to stop is much longer than it would be if it hits the wall. If you throw that egg at the wall, it's going to crack, right? because the amount of time that it's in contact with the wall is very, very short. And so this is a nice example of impulse. It's a nice example of impulse. So we'll come back to that another time. I was going to, the earlier version of this lecture from a long time ago, I actually had a whole section on how airbags are really important, because what that does is it increases the amount of time that, if there was a crash, that someone would slow to a stop. And so by increasing that amount of time, it lowers the average force, and hopefully makes the collision much safer for those involved. Now the next part of this lecture is about collisions, and there are 3 different types of collisions that this web page will bring up, so I encourage you to click on this web page, this link. And the first type is elastic, and as you can see here, it says kinetic energy is conserved. The second type is inelastic, and I can refresh this page and show that it bounces off, but not quite as hard as up here, and it kind of slows down over time, because every collision is losing energy, essentially. And then the last one is perfectly inelastic, which the 2 objects stick to each other. Sometimes this is called completely inelastic. So I don't know, different high school teachers say different things. Some people say perfectly inelastic, other people say completely inelastic. It's different names for the same thing, as far as I'm concerned. All right. So if you consider that elastic collisions, the kinetic energy is conserved, that means if you add the kinetic energies before the collision and you add the kinetic energies after the collision, that those 2 things should be equal to each other. Now in practice, this will never be 100% true. So for example, if you drop a ball on the floor, the fact that you can hear it hit the ground means that at least a little bit of energy has been lost to sound. And so whether this is 100% true for you or not, it's often approximately true. And so it's often very helpful to assume when things are bouncing off of each other. We're gonna continue to talk about this in the next lecture, by the way. Now, inelastic collisions. By the way, I should say that for elastic collisions, the momentum is conserved. The total kinetic energy is conserved, but the momentum is also conserved. So both of those things are conserved. And yeah, so that's the basic idea behind elastic collisions. Now, inelastic collisions, the momentum is still conserved. Yes, that's true. What is not perfectly conserved is the kinetic energy. So if you add up the kinetic energies of the objects before they collide and compare it to, and add up the kinetic energies after they collide, you will find that the initial kinetic energy is more than the final kinetic energy. So it's similar to the elastic case, but you're losing energy, just a little bit of energy each time. This situation is kind of hard to deal with, because you have to have some idea of how much energy is being lost at each collision. So in this course, we'll mostly be dealing with either perfectly elastic or perfectly inelastic. Not so much this case, inelastic collisions. Sorry about that. Now, perfectly inelastic collisions is arguably the simplest of the 3, because the 2 objects stick together, and because they stick together, that means that their final velocities are the same. And so momentum is conserved. In all 3 of these cases, momentum is conserved. But because in this case the velocities are the same, that means that you can write the right side of that equation as m1 plus m2, the quantity, times the final speed. What's interesting is that if you add up the initial kinetic energies and compare it to the final kinetic energies, they will always not agree. And I'll show you some examples of that in the next lecture, of 2 objects of the same mass. If they collide and stick together, the kinetic energy just cannot be the same as it was to begin with. So to summarize, again, perfectly inelastic is where they stick together, also called completely inelastic. Elastic is when they bounce off of each other and the total kinetic energy is conserved, whereas inelastic, they bounce off of each other and the kinetic energy afterwards is a little bit less than you started off with. Now the momentum programming lab is kind of fun. You basically have this ship that kind of flies around and it's trying to stick to another blob, and so the momentum coding activity is essentially applying the perfectly inelastic collision in 2 dimensions, not just 1 dimension, but 2 dimensions, which is actually not too bad. So you can look forward to working on that. The Pong game is actually an example of elastic collisions, except that instead of having 2 objects, it's just 1 object bouncing off of a surface. And so it's not too hard to figure out what the final speed has to be, because you know that the initial kinetic energy is the same as the final kinetic energy. Now I promised that I would convince you that when 2 objects stick to each other with perfectly inelastic collisions, that they lose kinetic energy, or that the kinetic energy is less than what you started off with. And that's pretty simple to think about. So you have some initial velocity here. Initially this thing is at rest. And then there's some combined object that moves together at some final speed. So, you know, m plus m is 2m. And so you can figure out what that final speed is just by dividing both sides by m, right? So you have mv initial over here, m times 0 over here, 2mv there. The final speed would therefore be half of the initial speed, right? That's fine. That's not too surprising, right? So again, final speed is half the initial speed. That's not too weird. Okay. What's interesting is that if you want to think about the kinetic energy, so the initial kinetic energy is 1/2 mv initial squared. The kinetic energy of the other object, which is at rest, would be 0. But then the final kinetic energy is going to be 2m times vf squared. All right, so you get a 2m there, but vf is v initial divided by 2. And so 2m divided by 4 is this, which is actually half of the initial kinetic energy. So, so no matter what, if these things stick to each other, the total kinetic energy is going to be less than when you started off with. So I go over all this to try to make sure, just to try to help you understand that perfectly inelastic collisions, you're always losing energy as a result of the collision. There's something about the sticking that makes this happen. Now, a fun application of this that relates to the worksheet is if you take a Nerf gun and you bounce the Nerf gun off, the Nerf bullet off of this thing, and depending on whether the Nerf bullet will stick to it or bounce, it may cause this block to slide further. So this is me from, I don't know, 2 or 3 years ago, the old building. And what I have is I have a piece of foam that's going to slide along this track, and I have my kid's Nerf gun, which I borrowed for the day. And I'm going to bounce the Nerf bullet off of it and also get it to stick. So in this one it's stuck, and I can go and I can measure how far it went. So that's 8 centimeters that slid, if it sticks. So do you think it's going to slide further if it bounces off, or is it going to slide less far, like 4 or something? So we can do that case, and so all I'm really doing here is I've rotated the foam around, and So clearly the bullet is not going to stick to the foam if the aluminum part is not there. And we'll see how far it goes. And it goes almost twice as far, right? So last time it was 8 centimeters, now it's like, gosh, it's more than 17 centimeters. So that's pretty impressive. So what's interesting about that is that it has to do with impulse, is that when the Nerf bullet sticks to it, the change of momentum is, the initial momentum to 0, but when it bounces off, the change of momentum is bringing the thing to 0, but then sort of accelerating it back again in the direction that it came. So the change in momentum is much larger, which means that it's a larger average force on this thing, or something like that. And so it actually slides further. So the worksheet for today is, you can work the math out on this and say, all right, well, this is the final speed after it collides, compared to it sticking. So this is if it sticks perfectly inelastic. This is if it bounces off. Now where this equation comes from, we'll talk about next lecture. They list it in section 9.4. But basically that's the premise behind the worksheet for today, which is that Captain America has 2 different modes for his shield, and he can either catch the bullets or he can cause them to bounce off. And the goal is to sort of, he doesn't want to slip backwards, right? So he's expecting he's going to slide to some degree because there's this tank bullet coming for him, but he doesn't want to slide too far. So in other words, there's some collision, Captain America has some velocity afterwards where he slows to a stop, and he wants to minimize that slide. So this is the basic idea behind the worksheet, and you'll have to use what we just learned to answer that question. Kind of like that. There you go. So that's about it for today. So good luck on the worksheet.